Today we will look at some problems about homework 8. For the first problem, we need to find components of the force to hold this VM. And we should apply the momentum equation to solve this problem. The first we sketch the survey like this one. Survey, CV, and then we sketch the force and momentum diagram. So force diagram. CV, and we assume the force in the y-axis, and this is the force in the x-axis. And we also need to sketch the momentum diagram. So we know this is m dot times v1. This is m dot times v2, and this is 30 degree. And we know that the mass flow rate m dot should be equal to rho times the q. And from problem, we know the SG of oil equals 0.9. So, and we also know SG oil should be equal to the rho oil divided by the rho water at the 4 degrees Celsius. And we know the SG oil equals 0.9 in this problem. And we also can find that when the water temperature at 4 degrees Celsius, we know that rho water should be equal to the 1,000 kilogram per cubic meters. And then we can determine that rho oil should be equal to 900 kilogram per cubic meters. And from problem, we also know the Q equals 0.9 cubic meters per second. So we can determine that the mass flow rate m dot equals 810 kilo per second. And then we apply the momentum equation in x direction. We know that the equation is sigma fx should be equal to the m dot times the velocity at outlet in the x direction minus m dot times velocity at the inlet in x direction. So fx should be equal to the f dot times minus v2 times cosine 30 degree minus m dot times v1. So, and we know m dot equals 810 kilogram per second, and v2 equals let me check, 33 meters per second, and v1 equals 29 meters per second. So we can determine that the Fx should be equal to the minus 46.6 kilonewton. Since the results is negative, so the force should act to the left. So yeah, and then we will apply the momentum equation in y direction. And sigma Fy sub y should be equal to m dot times v sub y minus m dot times vi sub y, and so we can get that Fy should be equal to m dot times minus v2 times sine 30 degree, and we know m dot equals 18 kilo per second, and the v2 equals 33 meters per second. So we can determine that Fy is F sub y should be equal to the minus 13.37 kilonewton. So things are without is negative, so the force should act downward. So we finished this problem. For the second problem, we need to find the components of force per foot of width to hold the vane stationary. The first, we selected CV. And then we sketch the force and momentum diagram. So for the force diagram, this is CV, and we assume that the force in the x direction, this is Fx, and the force in the y direction, Fy, and for the momentum diagram, this is CV, and from problem we know there is m dot m1 dot times v1, and there is m2 dot times v2, and this angle is 60 degree, and there is m3 dot times v3, and this angle is 30 degree. And then we apply the Ballooning equation. We know that the v1 should be equal to the v2 should be equal to the v3, qv equals 40 feet per second. And then based on the continuity equation, we know that the a1 times v1 should be equal to the A2 times V2 plus A3 times V3, since the area only depends on the width. So we can write the W1 times V1 equals W2 times V2 plus the W3 times the V3. And things we know, V1 equals V2 equals V3. We can determine that W1 should be equal to W2 plus W3, and from the problem, we know the W2 equals 0.2 feet, and W3 equals 0.1 feet. So we can determine that W1 should be equal to 0.3 feet. And then we apply the momental equation in x direction. So we have the minus fx should be equal to m2 dot times v times cosine 60 degree plus m3 dot times minus v times cosine 30 degree minus m1 dot times v, and we have fx equals v square times minus a2 cosine 60 plus a3 times cosine 30 plus a1. Since we need to find the force per unit width, so we can use the width to represent the area. So now the fx should be equal to rho times v square times minus w2 times cosine 60 degree plus w3 times cosine 30 degree plus w1. And when the water temperature at 60 degree Fahrenheit, we can find that the density of the water should be equal to 1.94 slag per cubic feet. And we know the V equals 40 meters per second, and W1 equals 0.3 feet, W2 equals 0.2 feet, and W3 equals 0.1 feet. So we can find that the Fx should be equal to 89.61 pounds force per feet. And the directions x to the left. And then we apply the momental equation in the y direction. And we have Fy should be equal to m2 dot times v times sine 60 degree plus m3 dot times minus v times sine 30 degree, and Fy equals rho v square times a2 times sine 60 degree plus minus the A3 times sine 30°. We have Fy to be equal to the rho times V squared times W2 times sine 60° minus W3 times sine 30°. And we know rho equals 1.94 slag per cubic feet, and V equals 40 meters per second, W2 equals 0.2 feet, W3 equals 0.1 feet. So we can determine that Fy should be equal to the 382.43 pounds force per feet. So in the direction x upward. So we finished this problem. For the third problem, we need to find the force required to hold the plate stationary. The method is the same as the previous problem. We select CV first. So this is CV, and then we sketch the force and momentum diagram. So for the force diagram, CV, and we'll show the force in the x-axis to the left. This is F, and then we'll show this is x direction. And we also need to sketch a momentum diagram. So for the problem, we know there is m1 dot times v1 is m2 dot times v2. And now we need to apply the momentum equation in the x direction. So we know that sigma f should be equal to m0 dot times VO minus mi dot times vi. And for this problem, we know that negative f should be equal to the m2 dot v2 minus m1 dot times v1, and the f should be equal to m1 dot v1 minus m2 dot times v2. And then we have f should be equal to rho times a1 times v1 square minus rho times a2 times v2 square. And from the problem, we know that the water temperature is 10 degrees Celsius. So we can find that rho should be equal to the 1000 kilogram per cubic meters. And we also know A1 should be equal to pi over 4 times d squared. A2 should be equal to the pi over 4 times to d squared. And from this problem, we know that V1 equals V2 equals 16 meters per second, and D equals 15 centimeters, should be equal to 0.15 meters, and small d equals 0.5 centimeter equals 0.005 meters. So we can get that F should be equal to 3.6 kilonewton. Since the result is positive, so the assumed direction is correct. So the force is to the left. So we finished this problem. For the first problem, we need to find the force of the water on the van. The first, we need to select CV and sketch the force and the momentum diagram. So for the force diagram, and we'll select CV. And we'll assume that the force in the x-axis is to the left, and the force in the y-axis is upward. And for the momentum diagram, and this is CV. Well, from problem, we know that there is the m dot times v1, and this is m dot times v2, and we know the angle is 45 degrees. And from the problem, we know that the van is moving at 7 meters per second, so the CV is moving. So we select a reference frame that is fixed to the moving van. So it's y, is x. So the reference frame is fixed to the moving van. And now we need to calculate the mass flow rate. And for the mass flow rate, we know the m dot should be equal to rho times A times V. And from the problem, we know the water at 10 degrees Celsius. So the density of water rho should be equal to the 1,000 kilogram per cubic meters. And we know the A is pi over 4 times d squared, and we know the D is 6 centimeters, equals to 0.06 meter. And for the velocity, V, actually the V is the velocity of water relative to the CV moving with 7 meters per second. So the V should be equal to the 20 meters per second minus the 7 meters per second. So the V should be equal to the 30 meters per second. And now we can get that the m dot should be equal to the 36.76 kilogram per second. And then we need to apply the momental equations in x direction. And from the problem, we know the fx, the minus fx should be equal to the minus m dot times v2 times cosine 45 degree minus m dot times v1, and we get that fx should be equal to the m dot v2 times cosine 45 degree plus m dot times v1, and v1 and v2 are the velocity of the water relative to the reference frame. And at the beginning, we assume that the reference frame is fixed to the moving van. So the v1 should be equal to the v2 equals 20 meters per second minus 7 meters per second. So equals 30 meters per second. And we also know the mass flow rate, m dot equals 36.76 kilogram per second. So we can determine that the fx should be equal to 816 Newton. And to the direction is to the left. And then we need to apply the momentum equation in the y direction. For problem, we know the Fy should be equal to m dot times v2 times sine 45 degree. And we know m dot equals 36.76 kilogram per second, and we know the v2 is 13 meters per second, so we can determine that the Fy is 338 Newton, and the direction is upward. And we know the force of the water on the van is the negative of the force of the van on the water. So the force of the water on the van is the F equal to the 816 minus 338 J Newton. So we finished this problem. For the fifth problem, we need to find the force that acts on the flangers to hold the band in place. First, we select a CV around the pipe band. CV, and we'll assume So y direction and x direction. And then we need to sketch the force diagram. So force diagram. Section 1, section 2. From the problem, we know there is pressure force P1, A1 to section 1, and there is pressure force P2, A2 to section 2. And from problem, we know there is a weight. So, and the direction of the weight is into the page. Actually, the weight should be equal to the weight of band plus the weight of water. And then we assume that there are required forces in the x, y, and z directions. So this Fx, and this is Fy, and the Fz, the direction of Fz, the direction of Fz is out of page. And then we need to sketch the momentum diagram. Section 1, section 2, CV. And from problem, we know at the inlet is m dot times v1. At the outlet, it's m dot times v2. And according to the continuity equation, we know that a1 times v1 should be equal to the a2 times v2. And we know from problem, we know a1 should equal to the a2, so we can get that v1 should equal to v2 equals q over the a. And from problem, we know the q is 0.35 cubic meters per second, and we know the a should be equal to pi over 4 times d squared, and we know that d equals 20 centimeter equals 0.2 meters, so we can get that the v1 equals v2 equals 11.14 meters per second. And then we write a momentum equation in each direction. So in x direction, we have that P1 A1 plus P2 A2 plus Fx should be equal to the rho times Q times minus V2 minus rho times Q times V1. Things from problem, the P1 A1 equals P2 A2 and V1 equals V2, so we can get that the Fx should be equal to minus 2 PA minus 2 times rho times q times v. And from problem, we know that the P equals 100 kilopascal, and the A P equal to pi over 4 times 0.2 square, and the Q equals 0.35 cubic meters per second, and we know the V equals 11.14 meters per second, and rho, the density of water, is 1,000 kilogram per cubic meters. Right? Yes. So we can get that Fx should be equal to negative 14.1 kilonewton. And in the y direction, we can get that Fy to be equal to 0. At the z direction, in the z direction, we have that the Fz should be equal to the weight of band plus the weight of water. And we know the weight of band is 400 Newton, and the weight of water in a band should be equal to the specific weight times the volume. And when the density of water is 1,000 kilo per cubic meter, the specific weight should be equal to 9810 Newton per cubic meter per second. And from problem, we know the volume, the band volume is 0.1 cubic meters. So volume is 0.1 cubic meters. So we can determine that the Fz should be equal to 1.381 kilonewton. So now we can get that the F vector should be equal to minus negative 14.1 times I vector plus 0 times J vector plus 1.381 times K vector kilonewton. So we finish this problem. For this problem, we need to find the force in the xy plane to hold the T in place. The same, the first we selected the CV. And then we need to sketch the force and the momentum diagram. For the force diagram, from the problem, we know there is the pressure force P1A1, and there is pressure force P3A3, and there's pressure force P2A2. And then we assume the required force in the x and y direction. So this is Fx, this is Fy. And then we need to sketch the momentum diagram. So for the momentum diagram, there is m dot times v1, and there is m dot times v3, there is m dot times v2. And then we apply the momentum equations in x directions. We have the fx plus p1 a1 minus p3 a3 should be equal to the m dot times v3 minus m dot times v1. And we can get that fx should be equal to the minus p1 a1 plus p3 a3 plus rho times q3 times v3 minus rho times q1 times v1. And we know the v1 should be equal to the q1 divided by the a1, and we know the a1 should be equal to the pi over 4 times d1 square, and we know the d1 is 15 centimeter, is 0.15 meters, and the q1 is 40 meters cubic meters per second. So we can get that the v1 is 2263.5 meters per second. And according to the continuity equation, we know that the q1 equals q3 plus q2, and we know q1 is 40 cubic meter per second, and q2 is 13 cubic meters per second. We can get that the q3 is 10 cubic meters per second. And now we can calculate the v3, and the v3 should be equal to the q3 over the a3, and a3 equals pi over 4 times d3 square, and we know that d3 is 50 centimeter, 0.15 meters, and we can get that v3 is 569.5 meters per second. And from the problem, we know the P1 is 100 kilopascal and P3 is 80 kilopascal. So P1 is 100 kilopascal and P3 is 80 kilopascal. So we can calculate that. Can get that the fx should be equal to the minus a4 minus a4 881 kilonewton. The direction is to the left. And then we need to apply the momentum equation in the y direction. Y direction, we have that Fy plus the P2 times A2 should be equal to m dot times minus V2. And we have Fy should be equal to the negative rho times Q 2 V2 minus the P2 times A2. And we know V2 should be equal to the Q2 divided by the A2, and A2 equals pi over 4 times D2 square, and we know that D2 is 7 centimeter equals 0.07 meters. And Q2 is 30 cubic meters per second, and the P2 equals 17 kilo, 70,000 kilopascal, and we know the rho is 1,000 kilogram per cubic meters. So we can get that the Fy should be equal to negative 233,859 kilonewton. The direction is downward. So we finished this problem. For the last problem, we need to find the propulsive force when the boat is not moving, and the propulsive force when the boat is moving at 30 feet per second. So first we select the CV, and this is section 1, this is section 2, and we assume that propulsive force is to the left in the x direction. And for the momentum diagram, we know there is m dot times v1, and there is m dot times v2. So for the first situation, the boat is stationary. So we have Fx is equal to m dot times v2 minus m dot times v1, and when the boat is stationary, we assume that v1 is approximately equal to 0. So we have that the Fx should be equal to m dot times v2. And we know the m dot should be equal to the rho times a2 times v2. And when the air temperature is 80 degrees Fahrenheit, we can find that rho should be equal to 0.00228 slug per cubic feet. You can find this value from the textbook in the table A3. And we know that A2 should be equal to the pi over 4 times d squared, and we know that d is 3 feet. And we also know the V2 equals 100 feet per second. So we can determine that the m dot should be equal to the 1.612 slag per second. And then we can determine that the Fx equals m dot times v2, and it equals the 1.612 slag per second times 100 feet per second. So we can determine that the Fx should be equal to the 1 61.2 pound-force. And when the boat is moving, we know that Fx should be equal to the m dot v2 minus m dot times v1, and we know m dot equals 1.612 slack per second, and v2 equals 100 feet per second, and v1 is 30 feet per second. So we can determine that the Fx should be equal to 12.84 pound-force. So we finished this problem.